and it did sync. It was just a couple of problems more. Were you able to see it, anybody, or not?
No.
All right, that's on me. I'll make absolutely certain it doesn't happen again. So any questions about any of the prior material before I start?
No.
All right, now we covered basically this. We solved the Maxwell equations for a single unknown, be it E or H, and we got the general solution for a plane wave. Then we looked at how plane waves propagate in two different environments. One, lossy dielectric, the other, good conductors, right? All right, we got wavelength, we got frequency, we got beta, alpha. We have the intrinsic impedance. And now what we're going to do is talk about two things that are important. The first is polarization of the electrical field vector and why it's important. And then we're going to talk about power flow. And then we're going to talk about reflections. Do y'all follow me on this? So I'm just telling you what the topics are I intend to cover. Now please be attentive to this. The book does this in a way it's a bit confusing. When we talk about polarization, of a wave, what we're really talking about is how the tip of the electric field behaves. Let me give you an example of this. Let me do it this way, because everybody, we're visual creatures. We understand a lot of the times images. So if this is an electric field vector, it's not, but just assume an electric field's pointing this way and it's oriented this way, right? If we froze time and we looked at the magnitude, this thing would go up, down, up, down. You all follow me? But it would always be aligned in this direction. Call that AX. It would go up, become a maximum, and down. And as time went by, this wave would move, but it would always have that polarization. Do y'all follow me? That's called linear polarization, where the electric field is always in the same direction. It just increases and decreases. Do y'all follow me? I'll give you the math in a second, but you have to understand what's going on. So if this is, let's say that the wave is propagating in the z direction, and this is x and y, and say z equals 0. Right? So this is the y direction, that's x. All right, now if an electric field at t equals 0 looks like this, then it gets bigger and bigger, then smaller and smaller, and turns this way, you all see that the electric field is polarized in only one direction, correct? Everybody? Now, if that same electric field was polarized in this direction, it would grow and decrease and grow and then decrease. That would still be linear polarization. It's polarized in only one direction. The electric field vector grows, hits a maximum, then reduces to 0. You all see this? Now I'm freezing, I'm letting time go by, but I'm freezing space. Another example. If you want the math behind this, I can give you the math, but I'm not sure it adds to anything. Suppose we had an electric field that grew, hit a maximum, and then it reduced this way. All right? That's still linear polarization. Y'all follow me? It's just taking this axis and shifting it, sort of. Isn't it, class? Matter of fact, if I wanted an equation for this electric field at z equals 0, I could say E here, if this was 45 degrees, it's just some E naught here, and you could put simply, this is straightforward, you could put cosine of omega t here, and then you could put just AX plus AY. You all see how that would be let cosine of omega, let omega t be 0 right here? Right, cosine omega t 0. The E field would have a value of E naught right here in the x direction, and would have E naught in the y direction. It would be at 45 degrees. Do y'all see that? Let time go by, let omega t here, that argument, go to 90 degrees, or pi over 2 radians. Cosine of that is 0. It would go to 0, right? Starts at a maximum and go to 0. You all see this? Then as the cosine becomes negative for values greater than pi over 2, then it would hit a relative maximum in that direction. Now that's a mathematical way to describe what I'm showing you there, right? If you want the electric field to have more of a tilt, one way to do this would just be put multipliers here. you could have plus 1.5 AY. Then you agree it would have more of a tilt. You agree that the angle would increase. But this is just methods of mathematically describing linear polarization at z equals 0. Y'all follow me? Now that's really the gist of linear polarization. It's just an electric field that is oriented in only one direction. And it doesn't matter if it has an AX and AY component. What I'm really trying to say is that it's going to have, it will only trace out a straight line, the tip. That's what I'm really trying to say. Y'all with me? That's linear. Then there is elliptical polarization and ultimately circular. I'm going to do circular first. And I'm going to level with you. I don't ask you about anything other than is it right hand or left hand. So I'll tell you what I'll ask you about. I'm not really worried about a lot of mathematics here because it doesn't lend itself to really helping understand or describe or design anything. Okay? In his book, he really gets into it. A lot of math statements. So suppose this is x and this is y, z equals 0. Now, another thing that can happen, and listen to me, that electric field can be propagating in this direction, but it can be composed of two waves. It can be composed in an electric field in this direction, and, well, really they're one and the same in a sense, and an electric field in this direction. But suppose the tip of that electric field traced out a circle. Now, just watch me. So I'm going to say if we look, that's a heck of a circle. If we looked at the electric field vector E, suppose it was tracing out a circle in that direction at z equals 0. Do y'all follow me? So if we put our thumb in the direction of propagation, I'm saying it's coming out of the board, then the E field would be going this way. Y'all follow me? That's actually called right-hand circular polarization. I'll get to that in a second. But first, what would be a mathematical way of describing this at z equals 0? Well, I could say it's really just what? Just think about what I'm doing. E naught here, right? And it could be cosine of omega t. Really, theta is omega t. It's the argument of cosine. And that could be ax plus, and then it could be sine of omega t ay. Now, just take a look at that and see if that makes sense. This is just one of, by the way, you can describe this mathematically in a whole bunch of different ways, but they all do the same thing. They trace the tip of this field vector versus time. I've got it going in the counterclockwise direction, don't I, class? And if you have a right hand, and you take your thumb and point in the direction of propagation, I'm saying the waves go in the positive z direction. So if that's x, that's y, z's out of the board. Y'all follow me? Take your right hand, take your index finger on your right hand, yeah, make a pistol kind of deal. Put it in this direction, and if it goes this way, that's called right-hand circular polarization. Y'all follow me on that? Because it's like you're closing, or I should say opening the door with your right hand. Correct, class? It should make sense. What do you think it is if it goes this way? Take a guess. Left-hand circular. I'm just making sure. All right, now, there's a reason they do this. And if y'all agree mathematically that should work, let's just play the game. At omega t equals 0, cosine is 1, so I have just E in the x direction, right? And the sine is 0, right? All right, now go to 45 degrees. Cosine of 45 is 1 over square root of 2, correct? Sine of 45 is 1 over square root of 2. The next point would be here. You see how it's going in this direction, right? Play the game again. Omega t equals pi over 2, right? At pi over 2, cosine is 0, sine is 1. Yeah, it's right up. You all see how this thing's going that way? Now, how would I make it go the other way? There's so many ways. Well, we could add a phase, we could do this and that, we could yak, yak, yak. How about that? That's another one. I mean, there's so many ways. That's the reason I don't get hung up in the math. You're going to see in Whitmore's book, he's going to talk about adding a z to the j and doing the phase domain. Don't worry about it. All right? Here's how you always do it. Take it in the time domain. Just listen to me. If you want to know what kind of polarization the wave is, and I'll try to do an example in a bit. Take Whitmore's description. It'll be in the phase domain. Put it in the time domain. You hear me? then let z equal 0 if it's propagating in the z direction, or x equals 0, or whatever direction it's propagating in, set it equal to 0, and then go back to the time domain. So multiply it by either j omega t, take the real part. Do y'all know what I'm talking about? Go out of the phasor, back to the time, but let z equal 0. And you're going to get something like this every time. Y'all follow me? And then just increment omega t by like pi over, I don't know, 4. Start at omega t equals 0, omega t equals pi over 4, omega t equals pi. It's going to rotate that way all the time. Y'all follow me? That's how you find out if it's right hand or left hand. That's it. And I'm going to tell you, there's stuff written, I mean, just pages of junk about how to figure this out. Forget that crap. Just get down to the basics. Bring it in the time domain, see how the tip moves. That tells you everything. It never stops moving in that direction. Y'all follow me on that? And here's why circular polarization is so important, specifically right-hand circular polarization, but we could say elliptical, that gets in the weather radar. When I have a right-hand circularly polarized wave and it's going out, and say it hits a conducting body, say that wall, it reflects back left-hand. Got me on that? So if it comes out righty, it's coming back lefty. Why is that important? I mean, Whitworth's book, he basically glazes over it. The reason is discrimination. I work with radar. I've done electromagnetics my whole career. I've done a lot of different aspects of it. But with radar in particular, this is important. Because if I send out a right-hand circularly polarized wave, and a guy tries to jam my radar or spoof me with a right hand, I know that ain't from a reflection from a real target. I know he's lying. So what happens is I send out my wave, right-hand polarization. This is oversimplified, but in essence, it's the truth. Now, anything that reflects back that's a left-hand wave goes through a filter, and my filter's frequency dependent too. Hear me on this, and they're easy. I mean, they're not easy, but you can build them. Then anything coming back that's got the right frequency, right polarization, now I process that information and see what the time delay was. All right? Now I can figure out distance to target, and by doing that several times, I can find velocity. You're going to find more about this in a bit. Y'all follow me? So that's why right-hand circular polarization is so important. Now, about weather radar, because I'm trying to make this something that's applicable to the real world. Y'all know what weather radar is, right? We have tornadoes down here, seems like, I don't know, 3 or 4 times a month in the summer, but tornadoes are something that are very problematic. You can have all the right ingredients for a tornado and not have them. And then you can have what you think is an insignificant amount of, atmospheric calamity going on, and one pops up. So here's how they do it. They do it with something called Doppler radar, and they look at the raindrops. When they send out a waveform, it is not, it's not circular, it's elliptical. And let me just show you what I'm talking about. Now, you don't write this down, just listen. The mathematics, if I want to make it elliptical, here's what I do. I just make this 1.5, it's elliptical. And when we're spoke, he's going to be talking about adding phase angles. Yeah, you can do all that. All of it works, but it doesn't really help with seeing what's really going on. Elliptical waveform just is tilted more, and it's elliptical. For instance, if you can have an elliptical waveform that looks like this, the tip would trace out that pattern. It's got more, doesn't matter the axis, just following this. I can make that happen mathematically very easily. Y'all follow me? Now, the reason they would want that is because the dominant scattering from raindrops is vertical. If they're falling vertically, do y'all follow me on that? So you would want the major component of the electric field vertical because you'll get a larger bang for your buck in terms of return. If you, this is going a little further, if I have a wire in this direction and I have an electric field in this direction and it hits it, it's going to get a maximum reflection back. You'll see this later. But if I have an electric field in this direction, perpendicular to the direction of the wire, then I'll get almost nothing. Y'all follow me? Now raindrops, graupel and all this other stuff, hail, they're basically water and they have conductivity. Not great conductivity, but they have okay conductivity at high frequency. So you know what a raindrop looks like, right? Teardrop kind of shape. They're elongated. You want to hit that thing with something that gives you a maximum bang for your buck. Now here's something that with Doppler radar is actually sensing the change in velocity of the raindrop coming at you, and that's further down the road. You've heard Doppler radar, right? They look for something called a, quote, hook echo. Have you ever heard of that? That's on the tail, right around where the high spinning things happen. There'll be this very, very, very obvious hook. I'll talk about that later. And I'm not a weather radar guy, all right, but I know enough because I deal with radar. Mine's all military primary, target IDs. Now, another thing they can do, and I don't know if they do it in the commercially available radars, but another thing they can do, if they're trying to discriminate the way the rain field's falling, they can change that ellipticity. In other words, change how that ellipse is oriented. And if they get more of a return at 30 degrees, they know the raindrops are probably falling this way, and that means the velocity field goes this way. Follow me on this? Now there's other ways of getting that. And there's all sorts of tricks, but weather radar is very, very important for a lot of things. Mainly when I was on the Eisenhower, I was a weapons consultant out there in the aircraft carrier. Weather is real important. We got a naval ship and an escort force out to sea because you don't want to run into really bad weather if you're going to plan an operation. So they want to know not just the 24-hour, but the 48-hour horizon very well. They want to know what's going to be there. Anybody been out to sea with a bad storm ever? Were you in the Navy?
I would.
Were you on a carrier, cruiser, or what?
Carrier, cruiser.
All right, that's, you don't feel anything on a carrier. Carrier is basically like being on land, except tilts up like 1 tilt per minute or so. And if you get off of those things, you've been on it for a week or two or more, you get what's called sea legs. Has anybody ever had sea legs? You have? All right, sea legs are kind of interesting. You never know you got them until you got them and you walk off the ship, and then all of a sudden, hey, you still move. Anyway, if you're in a smaller ship, it becomes a serious problem. You can't run the ship properly, especially minesweepers, stuff like this, smaller ships. Fishing vessels are horribly affected by radar. I mean by weather. Radar is what they need. Have you ever seen any of these crazy things like wicked tuna, what's the other one? Deadliest catch. Where these crab guys go out there and see, bad weather there sinks ships. These things aren't meant to take world-class storms. And occasionally one sinks. There was a movie made years ago about some of these guys were out fishing on a smaller vessel. They had George Clooney in it, I think. Remember this Perfect Storm? Anybody ever hear that? Basically, they got clobbered. Why? Probably because they didn't listen to the radio and they didn't have a weather radar, but both are important. So hear what I'm saying. Anyway, that's polarization in a nutshell. Now, I can tell you right now, here's the only thing you need to know. If it's propagating in the z direction, set z equal to 0, take it into the time domain and just plot the tip a couple of points. That's it. You don't have to worry about anything else. And I don't even ask this on quizzes usually. But left hand, right hand, that's it. Is it going to the left? And is the clock ticking this way, or is it clicking this way? That's the only thing I ask. Y'all follow me? I'll give you a few problems so you'll be okay with it. Trust me, it's not hard. Next thing we're going to talk about is going to be power flow. I know I didn't spend much time on this because it doesn't really warrant it until we get into an application of radar where you need to define in some way, shape, or form the return signal mathematically. Trust me, this will come up later. All right, so now what we're going to be talking about is power. Really, it's power density. All right, when you think of power, back in the days of circuits, if it was DC power, you found out that power was equal to V times I, right? Or if it was AC, it's 1/2 the real part of V times I conjugated. Do y'all remember that? That would be real power. Actually, V times I conjugate is called complex power. Y'all remember? How many of you have had Gross for power? If you've had Dr. Gross or anybody else for power, you know that term, complex power, right? There's a 1/2 that appears here because the V and I in this book will be peak values. Same with the E field. Y'all got it? So I'm just trying to show you your prior exposure to power. What are the units of power, by the way? Real power. Watts, right? Real power is in watts. Got me? Now, when you're talking about electromagnetic fields that are propagating plane waves, then power in the signal is usually given by something called S, and S is equal to E cross H conjugated. Now this is the instant, S here is really, I should put S vector as a function of ZT. It's really a function of spatial coordinates. The way they generally do that is just put X bar to indicate all spatial coordinates and time. This is an instantaneous quantity. Y'all follow me? Now if you have E, that's volts per meter, right? Everybody with me? E would be in volts per meter, correct? H is in, anybody? Amps per meter. So I have volt amps, watts, right? Divided by meters squared. And the units of this are watts per meter squared. And this is a power that's flowing. Now that's instantaneous. But as engineers, you've learned to appreciate RMS voltage, right? And average power. And RMS gives you an idea of what it would be at DC, or how much DC current it takes to do what you want, right? That's the reason we use it. It's root mean squared. So when we talk, this is called a pointing vector, by the way. It's a script S, and Whitmore Spokane not big on using this. What he uses is the average power. Can you read it or not? P-O-Y.
Is this spelled with a Y?
Yeah.
Okay.
Pointing vector, you can look at it up in his book, all right? I didn't spell it, I mean, somebody else designed that word, pointing vector. Maybe a guy's name, Ron. Okay, so the point, this is the instantaneous right here. This is the time domain. The actual value we care about is the average power density. All right, and the average power density is this. It's like that up here. It's 1/2 the real part of E cross H conjugated. Now you see the similarities between this and this right here, right? All right. It's a real times the conjugate of I, right? So it's the E field times the conjugate of the H field is the average power density. Now the reason we use the average power density is that is something where that gives you the average power that's flowing. So it's likened to, you know, RMS voltage kind of deal, all right? I mean, it's telling you something, not about the peak, but about the average, and that's the important thing. And this is assuming a sinusoidal variation too, by the way. It can't be just on, off, on, off. It's got to be a sinusoidal or cosinusoidal. So when we talk in generalities about this, just listen to me now. We have an E field that would be equal to some E naught, e to the minus alpha z. Let's assume it's propagating in the z direction. So we're going to have plus z direction propagation. It would be e to the minus j beta z in the AX direction. I'm going to be consistent with what he said. Y'all recognize that as the standard way we describe a propagating electric field in the X direction. This is Dr. Whitmore's choice, and I want to keep it simple. The corresponding H field from this would be equal to E naught over magnitude of eta. That's the intrinsic impedance, and I'll put it here. Intrinsic impedance is square root of j omega mu over sigma plus j omega epsilon, right? And by the way, gamma is equal to alpha plus j beta is equal to the square root of j omega mu over sigma plus j omega epsilon. So I'm putting these down here just to keep you straight, right? Now, this has a magnitude and an angle, right? In general, eta has a magnitude and an angle. So I'll put the angle down here first. It would be j to the angle of theta eta down here. And it will also attenuate as e to the minus alpha z, e to the minus j beta z, but we will be in the AY direction. Now, I could actually show you how to get h for a propagating wave from the equation. H is equal to what? 1 over eta, unit vector and direction of propagation crossed into the E field, right? We could do that. We've done it already, though, haven't we? Remember, we've done those? So I'm just stating it explicitly. Now, is everybody okay with seeing that this angle, e to the j, that, when I take it from the denominator to the numerator, it just makes e to the minus j? How many see that? All right, do y'all see it? I mean, I've got to make sure, because it's not, if you don't see it, don't worry about it, but some people, they'll come to me, how did you do that? Well, what I'm really saying, I'm going to say it for everybody's sake. If you have 1 over e to the j, like 45 degrees, that is really the same thing as e to the minus j of 45 degrees. That's the same. Trust me on this one. So I'm just going to take this up here and make it e to the minus j, and it's the angle, or really, I'll call it just theta here, sub eta, and it's really the angle associated with that. Y'all follow me? Got me? Now we're going to turn the crank and just do this. And you're going to see a couple things that are important. So when I say the average power, write this one down and start. Average power is equal to 1/2 the real part of E, right there, I've just rewritten the E field. Y'all follow me? Nothing fancy, right? Now I'm going to put in the cross product, so I'll do it this way. Now it's going to be crossed with the H field, but it's conjugated, right? Now y'all know the term conjugation. So what does that mean? If I have A is equal to, say, 1 plus J1, or square rooted 2 at e to the j pi over 4 radians, right? Isn't that the same thing? 1 has magnitude square rooted 2, it's at 45 degrees, or at j pi over 4, correct? Pi over 4 radians. Well, if I take A conjugate, what happens? Anyone? 1 minus j, right? Or it's square rooted 2 e to the minus j pi over 4, right? Y'all remember conjugation? How many do? In engineering, we use it all the time, so you have to be careful. That symbol is usually an asterisk, but I'm going to warn you. Occasionally in journal articles, they choose another symbol, so don't expect that to be universal. I'm just warning you on that, because those are mistakes I make. Reading a journal article, huh? That's not the conjugate, and they chose a different symbol, probably because they were using the asterisk to indicate something else. Right, but that's the common one. Now, then I have to conjugate this. So the E naught, the magnitude of eta, and e to the minus alpha z, those are strict real. You'll leave those alone. Y'all follow me? Now with conjugation, you see how I really have e to the minus j times the quantity beta z minus theta z? Everybody? I could add those two in the exponent, right? When you conjugate, they become positive. So I get e to the plus j beta z and e to the j plus theta associated with the actual intrinsic impedance, that's this guy. And I didn't put this down there, but this is in the AY direction, right? Again, I'm just doing this one time so everybody sees how it happens. Got it? All right. Now, if you look at this for 1 second, most of you will see this. You all agree the 1/2 is going to come down. I mean, it's there, right? I'm going to take it down here. Now look. This is strict real here, this first part. The E naught, see, I want the real part. See how that times that, this times this is strict real, right? But then I have this also, which is strict real, that's strict real, and that, right? So all these things have no phase angles. These two and these three, right? I can pull those out in front, can't I? Y'all agree with that? So I'm going to get E naught squared E naught squared, that's strict real, divided by magnitude of eta, right there. Then I'm going to have e to the minus 2 alpha z, because I have e to the minus alpha z times e to the minus alpha z. You all agree with that? Okay, guys? All right, now keep watching. I have e to the minus j beta z times e to the plus j beta z. That equals e to the j 0, doesn't it? Which is 1, right? Thank goodness. So that goes away. You forget about that term. They cancel. You still have that term. So I've got to leave that inside the real value. Real value of e to the j theta n. I'm going to get to that in a second. And the final, see, that's the only thing that's left when you do the real part, is that real part of that complex angle. But I have ax cross ay, which is az. Very good. And now, think about it. What is the real part of this? We've been going through this a little. We use a guy's name, the law after him. His name is Euler, right? Spelled with the E, U. So what is the real part of e to the j theta n? Right, sure. And here's what I'm doing. E to the j theta is equal to cosine of theta plus j sine of theta. The real part is the cosine, the imaginary part is the sine, right? So when I have this, this is going to be just equal to E naught squared over 2 magnitude of eta, right there, times e to the minus 2 alpha z times the cosine of theta, in the az direction. I'm going to make a couple comments, and the units of this would be watts per meter squared. That's the average power flow. Power density, I should say. It's in watts per meter squared, not power. You all follow me? Can you all see it in the back there? Far corner? Okay. Now, if you...
So we don't have to do anything with this suppressed j omega t?
No, this is average power. We're not in the time domain yet. This is average power. It's in the phasor domain, all right? But, you know, when you talk about, like, average power in your wall outlet, in your speaker systems or wherever, when they say 120 watts of average power, if you want it in the time domain, the frequency would be twice that, right? Still have a peak power. If that's the average power, do you remember how the peak power is going to go up by square root of 2? Do you all remember this stuff? And then you're going to have what? You're also going to have times the cosine of twice the frequency, right? 2 times omega t as far as how fast it varies for power. I don't want to worry about that right now. I want to keep the focus on this. This is in the phasor domain. Now, when we have this, take a look at this for a second. Obviously, this is something that decays with z, right? If alpha is non-zero, then as you go, the power decays that's actually flowing. What's happening is the power is lost in heating the environment, or really because of the conductivity of the region, it thermally would heat it. Do you all see that, class? And it's going down twice as fast as the E field goes down, you might say, correct? Because it's going down as e to the minus 2 alpha z. The cosine of theta n, I'm going to mention this, the angle theta n has to do with the angle associated with this right here, right? Now, if it was in a lossless environment, if sigma was 0, it would be just square root of mu over epsilon, the angle would be 0. Do you all see that? But as you get into a lossy environment where you get this, just listen to me. When I get a very good conductor, then j omega over sigma, the square root of j is really what? It's really e to the j pi over 4, 45 degrees, right? Y'all agree with that? Maybe I should say that. If you're in a good conductor, I'll make a little sidebar. Where sigma is much greater than omega epsilon, then you know eta is equal to square root of j omega mu over sigma. Do y'all agree with that? All right, well, square root of j is really what? That's e to the j pi over 4 radians, or 45 degrees, isn't it? See, that's the square root of j right there. And then it would be times square root of omega mu over sigma. So this could be rendered as square root of omega mu over sigma, right? And then it would be at an angle of pi over 4 radians or 45 degrees. Do y'all see that? This would be theta sub eta that would go in here. So the cosine of 45 degrees would be 1 over square root of 2, wouldn't it? Go with me? Now here's the thing. This cosine will have, it's usually, the closer you get to a lossless region, the closer the cosine of that angle goes to 1. As a matter of fact, usually it is 1. Y'all follow me? Like in the atmosphere right here. But when you get into good conductors or better conductors, it can go all the way down to 1 over square root of 2. That's the thing, my point. Got it? And that would be worst case if it was a very good conductor. You follow me on that, class? That would be power flow. Now that's really it in a nutshell. Until you do some problems, you don't see this. We are going to do some problems, but the final thing I want to talk about today is reflections from surfaces, and this is important. Go with me? How many understand what I went over? You look bored. It's hard to tell with math, but if you are, I understand. You've seen power probably over and over again, only that's really power density. It's in watts per meter squared. Now we're going to get to reflections, and this is important, and it's also something that can be a bit confusing. Okay. So this is going to be reflections. And I'm going to keep consistent with Whitmer's book. Please hear me on this. This one gets a little tricky. So what we're going to do is set up a coordinate system. This is the z-axis. And at z equals 0, right here, we're going to have a boundary. This is going to be medium 1, and this is medium 2. All right. Now, both media have parameters. I'm going to let this one, right here, I'll just show you what I'm going to do. I'm going to make this air, so both epsilon relative equals mu relative equals 1 and sigma is 0. And what I'm going to say is I have an electromagnetic field propagating in this direction, and it's oriented in the x direction. This will be x. And I'll just call this E, and this will be called E incident. In Whitmer's book, he calls it E sub I. It's an incident wave. Now, we'll get to the mathematics in a second. Y'all see this? It's a plane wave propagating this way. The electric field is parallel to the boundary it's going to strike. And media 2 will have some value that's not 0 possibly. It's going to hit, and then there's going to be a reflected wave going this way. And that's going to be E reflected. Makes sense to everybody? Got an incoming wave. It hits this boundary, some of it reflects. Got it? It's going to reflect back in the z direction, but some of it actually gets through here. So some of it goes through, and that's going to be a transmitted electric field. Got me on that? Okay. So when I look at this, I'm going to use the standard convention Dr. Wentworth does over here. I'm going to say the incident field plus the reflected are in region 1, and the transmitted field is in region 2. So when we look at this, the incident field would have the form of some E naught incident, e to the minus, and I think he uses gamma, but it doesn't matter. E to the minus gamma 1 to z, ax. And it would have a corresponding H field incident, which would be E naught incident over eta, and I'll call this eta naught here, and it would be times e to the minus, well, if it's air, it's just beta anyway. I might as well just go ahead and make it minus j beta 1. Make this minus j beta 1 ZAY. Now y'all see what I've done there. That's the incident field in the standard way Dr. Wentworth's book likes to write it. And I made it air so I don't have to worry about that alpha term. Okay? Don't worry about the intrinsic impedance being complex. That's just eta naught. Got me, class? That's the wave coming this way. Now the wave reflected will be equal to some E naught reflected, E, but it's going the other way, so it'll be plus J beta 1 Z in the AX direction. And H reflected will be equal to E naught reflected over eta naught, but it's going to be minus because it's going the other direction. Remember, the ratio of E naught over H naught for the positive going wave was eta naught, and for the negative going wave it had a negative. Do y'all remember that or not? This will have a negative sign, and it will be E to the J beta 1 AY. So that's the incident, that's the reflected field. Follow me? This is consistent with what he's doing. Finally, the transmitted field will be E naught transmitted, or E transmitted, pardon me. There's going to be some E naught transmitted here. It's going to be times E to the minus J beta 2 times Z times E to the minus alpha 2 Z in the AX direction, and H transmitted will be equal to E naught transmitted over the magnitude of eta 2 times E to the minus J beta Z, E to the minus alpha Z, alpha 2Z, and it's also going to be E to the minus J, and this is the phase angle associated with eta 2. And it would be in the AY direction. That's a lot of writing, but you gotta get the math notation down right to do this. Y'all with me? Now the way we do this, thank God, and the reason I set this boundary right at z equals 0 is now we make z equals 0, and magically all these exponentials go away. Yes, sir?
Is that magnetic field on the bottom reflected supposed to have a z with the beta?
Yes.
Okay.
And that is my fault.
All good.
All right, now what we're going to do is we're going to look at what happens right at this boundary. So now we explore, and this is the key thing. Now we look at z equals 0. So at z equals 0, it gets rid of all those e to the j beta things, right? Because z is 0, e to the j 0 is just 1, isn't it, class? So that's the reason we put the boundary at z equals 0. And then when we work through it, we know two things. Do you remember from EMAG 1, whenever you had a surface where there's a discontinuity in parameters, that the tangent electric field on one side was equal to the tangent field on the other? How many remember that? And we remember the H tan, right? The H field, tangent H field on one side was equal to the tangent H field on the other if there was no current at the surface. Do y'all remember that? So it's called E tan 1 is E tan 2. So here we say E tan in region 1 is equal to E tan in region 2. And what is E tangent in region 1? Well, in region 1 you have an incident and a reflected field, correct? And they superimpose at every point, and they superimpose at z equals 0 just on the other side of that boundary. So we say that E naught incident plus E naught reflected is equal to E naught transmitted. That's your first equation. The only thing I did is put down what I've written up there and set z equal to 0 and equated them, right? Incident plus reflected is the total field on the region 1, and transmit is the total field in region 2, and they're tangent. Do you all agree with that, class? All right. The second thing I do is take H tan 1 is equal to H tan 2. Well, the tangent H field in region 1, now take a look at that. That's going to be at z equals 0. E naught incident, and it's going to be over eta naught, right? But then it's minus E naught reflected over A naught, eta naught is equal to E naught transmitted over eta naught. You all follow me? And again, I've just equated the H field on the incident side, or region 1, equated it to the H field in region 2. Can you all see this okay? Now we simplify. I can replace, and you don't have to write this down. You're going to see the net. Yes, sir.
Would that be eta naught on the?
Sorry,
Eta
eta
two, right?
2. I'm so sorry. Thank you so much for that eta 2. I apologize. You all with me on that? All right. I feel you're right. Now, I'm still watching my clock here. And when I do that, because I've equated these things, now what I do, see that eta transmitted there? I stick in this right here, and I get E naught incident minus E naught reflected here times 1 over eta naught is equal to, and then here it's going to be E naught incident plus E naught reflected over eta 2. You all follow me on that? Just replaced what? This eta naught transmitted with that there. Y'all follow me? Everybody? Now, you can see I have two unknowns, right? But we don't really care about either one of those unknowns identified by themselves. What we care about is the ratio. And it's called the reflection coefficient. Put this down here. It's gamma, and that's eta 2 minus eta naught over eta 2 plus eta naught. I'm going to explain something. This reflection coefficient is the ratio of the reflected wave's magnitude to the incidence wave's magnitude. Do you remember reflection coefficient from transmission lines? How many do? Well, I'm glad. Now here's the key with this. I'm putting it down. I didn't work through it because I'm out of time just about, but I want you to understand this. The way I always tell people to do this. If you're worried about reflection coefficient, the simple thing is go for the impedance you're going into, eta 2, subtract the impedance you came from, eta naught, and then divide by the sum. That will be the reflection coefficient whether you're in transmission lines or if you're talking about propagating waves. You got me on that? I don't go yet. The transmission coefficient is equal to 1 plus the reflection coefficient. Remember that from transmission lines class?
Is that a tau?
Yeah, it's trying to be. It's a tau. All right, it's transmission coefficient. And what that is the ratio of the transmitted field to the incident field. Okay? You can do it this way. You can say this is equal to 2 eta 2 over eta 2 plus eta naught. And that will be the transmission coefficient. Promise you it works. All right? Always works. And really, since these are ratios, you can find the transmitted and reflected electric field magnitude. And I am about out of time. I didn't get a chance to do a problem with the polarization, but I think you'll find it trivial. I'm going to give you homework. For the quiz on Friday, I'll give you a problem related to, I may ask for wavelength, something like this, but I'll ask for power and possibly the reflected field's magnitude, something like that. So it'll be on this as well. It's going to have 3 or 4, everything builds in this class. So you have to understand the first lectures to understand these lectures too. Okay? So I guess I should say comprehensive, but you're going to get something on this issue. It's usually 3 parts. For the quiz Friday, when you get here, I don't know if this is feasible, but try to spread out as much as possible. I don't know what else to tell you. As far as I know, it's a go. We'll be here on Friday. Some people may have excuses, and we'll take care of that. Are you going on the game?
Not this week.
All right.